reptiles in this session, so we're winging it. I want to talk about some work that I've been doing in collaboration with a bunch of other folks, and so I want to point out their contributions to this work on this really fantastic group of great Antillean boas. So many of us are familiar with interesting evolutionary patterns that occur on islands, and one of these patterns is the sort of familiar island rule. And so this is this idea that that when animals colonize islands, that they might change in body size, either become larger or become smaller. And so I want to show what this looks like. In many squamate reptiles, we have good examples of this process of the island rule. And this paper just came out, Darren Card and friends, showing this repeated evolution of small body size in boa constrictor, or now boa imperator, off the coast of Central America. In other words, these boas had colonized these islands and subsequently become small. And this has happened independently, independent colonizations of these islands, independent evolution of small body size. And this is thought to be an adaptation towards arboreality and feeding on migratory birds. In other words, it's an adaptation towards a sort of a novel food resource and also a limited food resource on these islands. So we see many patterns like this in squamates, and including some really interesting ones. So I work on the greater Antillean boas, and these are really a fascinating group of about 12 species distributed here in the greater Antillean Islands, as well as the Lucayan archipelago, which is comprised of Bahamas and Turks and Caicos. 12 species, and even though it's a modest radiation rising from a colonization event from South America in the Miocene, it's only 12 species, but there's really a fantastic amount of morphological and ecological diversity among these few species, all different colors, shapes, and ecologies and life histories. One of the most interesting and readily apparent patterns that we see is this really big differentiation in body size among these species. So we have the examples of really giant species like the Cuban boa, which can reach up to 4 meters long, and then really small species like this northern Bahamas boa, which is less than 1 meter long, full grown. So this is a really dramatic difference in body size among these within this genus. Some of these have really evolved some pretty spectacular morphologies, and in some cases very similar to mainland species that are completely different. So this is a Hispaniolan vine boa, which really doesn't look much at all like a boa, in my opinion. It looks much more like the Central American Nematodes, which is a colubrid snake. Ecologically similar animals, and you can see that they've evolved for sort of a similar gross morphology. In other words, they're arboreal, they're slender, and they have these big heads. So this pattern of body sizes has an interesting distribution. So we see that some islands like Cuba and Jamaica have a single large species of boa. But where it gets really interesting are islands like Hispaniola, Puerto Rico, and Lucayan archipelago, where we see large species and small species co-occurring. So within Hispaniola, for instance, we have a large species and 2 small species. Similarly, in Puerto Rico, large species, 2 small species. In the Bahamas and Turks and Caicos, large species, 2 small species. So what's going on here? Well, the first thing we needed to do was to generate a phylogeny to get a handle on what might be happening within this group. And so we constructed a complete species tree for all the West Indian boas, and this took a really long time to get these samples. Some of these animals are really hard to find. They live in places that are hard to get to, so this was the first step, and it was really the longest, many years to get these samples. So once we have a phylogeny, we have these really interesting questions that we can ask, and so we use phylogenetic comparative methods to ask some of these questions. And the first one is, if we have these species, some are large, some are small, did the small ones evolve and then subsequently disperse to these islands, or has that small body size evolved in situ on different islands? And we can test that by looking for phylogenetic signal body size. So here's a cartoon where I've mapped the body size as a continuous character on the phylogeny. And what you can immediately see is that small body size is distributed throughout the tree. We can test this using a variety of methods, including Pagel's lambda. This is a metric where 0 would be an indication of no phylogenetic signal in this character, in other words, body size, whereas 1 would be a really strong phylogenetic signal. In other words, what we're testing for here is, did these species, these small species, evolve independently, or did they share a common ancestor and then subsequently move to different islands? And what we can see is that they've evolved independently. We can do a variety of other things, including parsimony analysis, to try to get an estimate of how many transitions between large and small body size have occurred. And so we can actually map these transitions across the tree. And what you're seeing here are representations of these islands. So you can see here that in Hispaniola, we have the independent evolution of small body size relative to Puerto Rico, relative to the Bahamas. So now we're seeing repeated evolution of small body size within this modest radiation. We can do other things like estimate autocorrelation. This is Moran's eye showing no phylogenetic signal. So deterministic evolution of small body size, that's a possibility. But what else do we want to know about them? Well, there's these interesting differences. So large boas tend to be generalist species. They utilize a variety of habitat types and a variety of prey types. But small species tend to be specialists, ecological specialists. So they're using certain types of prey and certain habitat types. So we want to know, is there any sort of relationship between this reduction in body size, this evolution of small body size, and the evolution of specialization? And so if we look at this chart showing small species on the left and large species on the right, we want to ask these questions about either habitat specialization, like arboreality, or dietary specialization, like moving to a diet almost exclusively composed of anolis lizards. And so we use the threshold model to test this idea. And this is a model that allows us to basically model a discrete trait, in this case, this discrete trait of generalist versus specialist. And what we're modeling here is the evolution of the discrete character, but it's being modeled by these underlying liabilities that might represent any number of continuous traits. So this is really useful in the context of these sort of polygenic or complex discrete character traits that might be comprised of any number of different underlying continuous variables. And so what we find is, what we're asking is there correlated evolution between body size and specialization? And so we use a variety of methods to estimate posterior liabilities for this relationship. And we do this, we iterate it a number of times, 1,000 times in this example, and we're looking for mean correlations in body size and these liabilities. And so what we find is that, indeed, for habitat specialization, body size is correlated with habitat specialization. So small species become habitat specialists. And we can see this if you just eyeball these data. So here's the threshold right here between specialist and generalist. And here's body size on the x-axis. So if you look over here, the small species are specialists and the large species tend to be generalists. So that's a pretty strong pattern for habitat. We see a similar pattern, although not nearly as strong, within dietary specialization. And one of the reasons for this might be that we don't have great dietary information for a couple of these species because we just don't know enough about the natural history. So we think that transitions to small body size are consistently associated with an increase in habitat specialization. Okay, moving from generalist to specialist is associated with evolving small body size. And we're seeing this happen across different islands, independently. So then we want to know, okay, is this process happening similarly on these different islands? So is ecological specialization correlated with something that we can think might be important in this process, such as head shape, so trophic morphology in these boas? So we took a variety of measurements of the heads of these different species. We analyzed them using phylogenetic PCA analysis. And what you can immediately see is that we might expect for the small species to sort of be clumped together within this three-dimensional PC plot. In other words, the specialists might have a very similar head shape. We might expect that to be the case. We're not seeing that at all. So in this case, we have the generalists sort of distributed throughout this three-dimensional space. We have the specialists, in other words, dietary and habitat specialists, sort of the dual specialists, not really clumping together. And then the habitat specialist and dietary generalist, similar situation. So there's no clumping within this plot. So that tells us that the head shapes really aren't that similar. So the animals are getting small, they're evolving specialization, but they're not doing it in terms of producing similar head shapes. So we wanted to dig in a little deeper and ask this question: does ecological specialization affect the rate of cranial evolution? We call this a rate by state method. So what we're doing is estimating rates of cranial shape evolution and the ancestral habitat or diet liability from this threshold model analysis for each node of the tree. And so in this case, the rate is the rate of head shape evolution, and the state is the state either of the ancestral habitat or diet. And so we're going to compare this to a Brownian process whereby we're modeling independent evolution of these liabilities and head shape rates. And so what we find is that ancestral habitat, which we call substrate in this particular example, this specialization is associated with elevated rates, elevated evolutionary rates for head shape. We don't see a strong relationship with diet as we do with substrate or habitat, and that's again probably relating to some of the limits of the information we have in natural history of these species. So to sort of summarize this, we have this deterministic process happening in this modest radiation of 12 species. We have the repeated evolution of small body size happening on different islands or island groups. We also have a repeated evolution of specialist ecomorphs, and this is associated with that transition to small body size. So this is a pretty interesting pattern. It's a very strong pattern that shows up even among a relatively small group. We also have the stochasticity element, and that's this increased rates of head shape evolution correlated with this transition to small body size. So the transition is producing specialist ecomorphs, but it's happening in a different way, at least with regard to trophic morphology. Okay, but hold the phone, because we're not finished yet. That's a nice little story, but something interesting has happened in the last year. And so it was foretold that there might be more species of boas in the West Indies. And sure enough, there are. We discovered a new species last year that we named the Conception Island silver boa. And so now we have this additional species to add into this analysis. And so we might want to know sort of how does it influence what we know about the evolution of this group. Well, it turns out that based on the fieldwork that we've done, the Conception Island silver boa is an arboreal specialist. It's a small species, less than 1.5 meters long, and it's a bird specialist. So this is an example of a habitat and dietary specialist, but